All right, AP2, here's your lecture. Yeah, I'm gone. Got into a car wreck today, leaving school. So you got to be careful leaving school because there's an SUV turning in, and I was pulling out, and there was a white car right behind the SUV that I did not see, and jacked up the axle to my car, and gonna get a rental car tomorrow. Couldn't get one today, so I'm gonna be out. So I'm okay. If you're worried about how I am, I'm okay. Thanks. Um, if you just said, "Oh my God, is he okay?" But yeah, I'm alright. Just got some bumps, bruises, scratches, and all that other crap that you get whenever you get hit by a car and you experience a lot of acceleration all of a sudden, and your car goes from, straight going one way to 90 degrees another way. But yeah, so we'll see if I'm back later on in the week. I'm not sure what the extent of my injuries is, but nothing, not a lot of bleeding at the moment, not a lot, and nothing broken. I don't think. So anyway, you got homework online. Here's some help with that. We did ray tracing the other day, and I'm just going to do some of that again, but I'm also going to add some equations to it. So if you remember the concave mirror has, if these are mirrors and light's coming from the left side, let me actually use a different color for this part, then light does something when it hits a mirror. Usually it bounces off if it's the right kind of mirror. You might think that's silly, but some light does not bounce off some types of mirrors. There are many types of mirrors. Anyway, so light coming into this one, this is actually a convex. Ooh, shaking. But if the light hits this one, it bounces off, but it does bounce off in a certain pattern if it comes in that horizontal, and the pattern is away from this focal point that this convex mirror would have on the other side of the mirror. And that doesn't really make a lot of sense, but if you think about a mirror as like a part of a circle, here's the circle, here's like the center of the circle, and the focal length would be somewhere over here. So this one, you have the light coming in, and it's going to want to reflect downwards to a certain point, and that's what we did on Monday with the burning of the wood. We used a nice concave mirror to focus the light down to a single point. You kind of saw how powerful the sun was. Taking about a meter by a meter of sunlight, focusing it down in one spot, it's pretty dang powerful. So, checking out the first diagram, remember that this arrow is actually, I'm trying to find my blue pen. This arrow is not just an arrow pointing up into the sky. This is our object. If this was a person, it would be a person that looks like this. And Vlad the Impaler came by and impaled them on that arrow. Anywho, so it's going to create an image from this mirror, and we need to remember what the concave mirror does. So one of the lines that we're going to do is the top one from the top of the object through the center curvature, and it just bounces straight back, really. Just goes, comes straight back. And then you have another one, and that's going to be, let's use red for that one. And this other one, not in any particular order, but we'll do it like this. It's going to start off horizontal, and if we remember what the concave mirror is good for, it's good for burning crap, so it's going to reflect this down to this point. And I'm going to be very upset if nobody said, "Oh my God, is he okay?" That's right. Last line is going to be the check line. Last line is going to be the check line. It's going to go from the top of the object straight through that focal point. And once it hits the mirror, just like how the other one that was going horizontal went to the focal, if it goes to the focal first, it's going to go horizontal. And this third line is not essential, but it will let you know if you are right on the money. So all three lines right there did converge, and that would be my person. That would be upside down. They would be reduced though, and they'd be inverted. They'd be upside down, inverted, and reduced. So if you were to actually talk about something called magnification, usually denoted by a capital M, we're talking about the height of the image divided by the height of the object. And in this case, my magnification would be negative and less than 1 because the thing's flipped upside down and it's smaller. Alright? It's also equal to negative di over do. What the heck is di and do? Well, that's the distance that the image is away from the mirror, and that's the distance that the object is away from the mirror. So this negative here, if you look, the distance of the image is right there. That's positive distance. That's actually where the light's going. That'll make more sense later on. distance of the object is right here, distance of the image is actually less than the distance of the object, so we get a ratio that's less than 1, and the negative still sticks. If the image happens to be over here on the side where the light shouldn't be for the mirror, then that image distance is going to be negative. Okay, so we're going to see that right here. Now, if we look at this, I have an object right there. The first line is going to be that line through the center of curvature. I used blue before, so I'll use blue again. And it's going to go somewhat like this. I'm going to draw it all the way through. I'm going to try to use dotted lines on the other side because I know that it's a mirror and my light shouldn't really go through the mirror. So it's going to hit, bounce back over here. It never really gets over here. And then my red line was my horizontal line. And it goes horizontally, a little bit high there, that's okay. And it should bounce straight back through this focal point. But I'm going to trace that reflection line all the way through here. Okay. And the last line was, I guess, the black line. And I'm going to draw this one through the focal. And we know that when it hits the mirror, it should straighten out. And so it's going to straighten out like this, but I'm going to trace that straightened out piece all the way through this side. And so if you notice, all three lines sort of come together. Remember, my red line kind of screwed up, plus my drawing is kind of small. But they kind of converge somewhere over here. And this image is going to appear to be behind the mirror, and it's literally where your eyes are going to have to focus, behind the mirror to see it. It's going to be bigger than the object was, and you know, if you look at the magnification equation again, height of the image is greater than the height of the object, so your magnification would be greater than 1. And this distance of the image, this is di right here, but it's actually a negative di because the light never really gets behind the mirror. Okay, so again, if it's going to a place, or if it's at a place where the light doesn't actually go, it's not supposed to be there at that moment, then you use a negative thing. And so this image is actually a virtual image. Number one, because it's right side up. Number two, because you can't possibly put a piece of paper here and project it. The image that was in our first diagram, you can. You actually can project that onto a piece of paper that you put there, as long as you're not blocking the object in the first place. So that would be a negative di. Now if we come on down here, then we got the convex mirror. A convex mirror is kind of like a shield. So if you imagine a shield, light's going to bounce off of it away from the shield. So looking at this, let's put an object, and convex mirrors are often used in like convenience stores or gas stations, parking garages. You can kind of see around corners. Kind of wish I had that earlier. But that's besides the point. But convex mirrors, if they're curved like this, would have a focal point somewhere on this side. So I'm going to say, here's my focal point. And if you notice, it's on the side that light doesn't really go, so it's probably going to have a negative d distance of the focal point associated with it. But, oh, I got to draw one more. Not only the focal point, but I also need to draw the center curvature. So the focal point was about 2 inches, and so my center curvature is going to be all the way out here, another 2 inches. There you go. And so I need to draw my first line straight to that. So this is kind of big, but it's alright. So all the way over here, sorry, using blue, I know. Here's blue, there we go. And I didn't use dotted lines, crap. That's right. Anyway, my second line is going to be that horizontal line. Notice how these kind of work all the same way. But what I know about this horizontal line is that it's a convex mirror. And convex mirrors are like shields that will deflect it outwards. So I should deflect it outwards, but there's a method to the madness in that the deflection should be lined up with the focal point in the first place. So this reflection should be able to be traced back through like so. Okay, it should go straight to that focal point. That gives us a part where our lines cross, and we're going to try one more line here. The last line needs to make use of that focal point to go straight towards it, but being a mirror, it never really gets there. So it just bounces off, and if it bounces off horizontal. And so it should go that way, but we can trace that back. Remember, this is ray tracing. And so right here is where our image should be. We would be doing this lab in class, but I'm sorry. I thought a car accident that pretty much totaled my car warrants a day off. But this image is virtual. It's right side up. It's reduced. And so as far as our magnification goes, remember that's HI over HO, high over ho. HI is smaller, less number. HO is bigger, bigger number. We get a number that's probably going to be a decimal here, plus it's going to be positive because the thing didn't flip upside down. If you look at the other part of the magnification equation, the distance of the object is always positive here. Okay, it's a little bit bigger than the distance of the image, so if you do that ratio alone, you get a number that's less than 1. And the distance of the image is actually behind the mirror where light doesn't really go, so that would be a negative number. So negative cancels out, and so again we get some decimal number here. Okay, now moving on to lenses, I'm actually going to come back and do a little bit of math too, but that'll be at the end because I know you guys love math. Hey Kendall, how's it going? So this one is a lens, and what we know about lenses is that light passes through them and it refracts. Refraction is the bending of the light due to it moving at different speeds. And here we have two lenses. One is a convex lens, this first one, and the second one is a concave lens. Yes, I do have these on my desk if the sub will let you touch them. They're right by my dock cam. But we have the convex lens, which is like a magnifying glass, and what we know about magnifying glasses is that, hey, let's play some music. So the light will go down to a point, and that point is known as the focal point. So you can burn stuff with magnifying glasses. That's what's so good about them. Alright? And due to the fact that you can burn stuff and it actually will flip the image upside down, that means you can project stuff with the magnifying glass. Okay? But the things that you project will probably be over here. If the things that you're trying to project are over here where the object is, that's not going to be possible. Alright? The concave lens, though, it's not going to do what the magnifying glass can do. It's going to do the exact opposite. So it's going to make the light go outwards. But again, there is a method to it because these lenses also have a focal point. They're just on the other side. Alright, so while this light does go out, we should be able to trace it back to this focal point on the other side of the lens, the side that the light is not currently going to. So we'll use that fact to kind of draw these two. The same rules apply, except you got to remember what you're using. So, let's see. First line's the easy line. We go from the top straight through the center. Okay, and this is going to be the center of the lens, because the center of the lens should not bend it in another direction. It should just go straight through and keep on going. As far as the light goes, we're going to talk about the red line. The red line goes horizontal. Check that out. And it's a magnifying glass, and magnifying glasses are excellent for incinerating ants, which means that this light would have to go down to the focal point. There you go. Lost a little bit of my pen there, but you can see that. And then we have the other line, and we're going to have to use this focal point that we haven't used yet, so you got to keep your head about you. There you go. And then if you've already gone through a focal point, most likely you're just going to straighten out. This is your check line. So somewhere over here you're going to have an upside down image. It will be real. It will be reduced. And again, here's your magnification equation. HI over HO. The image is upside down. It would be a negative HI, which should give you a negative magnification. Or I have negative DI over DO. The distance of the image is positive since it's really where the light's going. Positive number on top. And a positive number for DO. So it would give you, again, a negative magnification telling you that the thing flips upside down. Okay. Yes, I am hiding another equation if you're wondering. So right over here, we have another convex lens, focal and focal, and we'll draw the ray diagram for this one. Feel free to fast forward if you've already been doing that, then I don't care. But that light goes straight on through the center, got the red line that attempts to go straight, but what we know is that when it hits the lens, it will refract and it'll actually try to bend, and it'll bend downwards down here. But hey, this is ray tracing, so we're going to trace that ray back over to the other side. And then you've got the last line, and the last line is going to go through the focal point that you haven't used yet. It's going to go through this top here. And if it's already gone through a focal point, it's going to straighten out. So this thing's going to straighten out as best I can, but we're going to ray trace it back. And so right around here is where our image is going to be, but I'm going to do a dotted line for that image because this is a lens, right? Lenses let light pass through them, so if the light's over here, the image being over here, that's not where the light should be, so we could never project it. It's an upright image, and upright images we know are virtual. Okay, and it's also enlarged, all right? If you look at the distance of the image compared to the distance of the objects, the distance of the object is smaller compared to the distance of the image from the lens, all right? So this whole magnification thing still applies, this negative di over do, but in this case the distance of the image is negative because it's not where the light's supposed to be going. The light's over here, it's projecting through, alright, so those negatives will cancel out. Last one's going to be this concave lens here, and this is kind of the weird one of the bunch because you don't use concave lenses too often. But concave lenses will have a focal point on either side. There you go. Focal points on lenses exist on either side. Light goes through. You can flip the lens around. It should go through the exact same way the other way. And we'll place an object out here. And I'm going to make it rather large. Oop. And so the first line that we do is going to go straight through the center. Unrefracted, really, unchanged in direction. Well, refracted while it's in the glass, but otherwise unchanged. We'll do a horizontal, which is like so. And you got to think about what kind of lens this is. This is not a magnifying glass. This is the exact opposite of it. So the light doesn't go down, it goes out. So it should go out like this, but again, method to the madness. It should be traced back to F on the left side. Okay, and that gives us an intersection point right there. Then your last line is going to make use of that focal you haven't used yet. This is going to be one you're going to have to practice a little bit, I think. And that packet that I gave you the other day, you should still have it, right? If you don't, there are like 3 on my desk. But we have a line that goes straight to the focal point on the other side, but it doesn't quite get there. It gets straightened out first. And we can trace that straightened out piece on back, and we should have an image that's right over here. But again, hey, this image is not where the light's really going. It's a virtual image. It's upright. It's reduced. And it should also work with another equation that I'm going to introduce to you by going back to our first page. So the other equation that you need to know for this ray tracing stuff is going to be this one. This is the mirror or lens equation. 1 over f, the focal length, is equal to 1 over do plus 1 over di. This is not the lens maker's equation. I believe the lens maker's equation has n in it, the index of refraction. So just to take a look, we're just going to double check this at the very end of this video. So let's see if this actually fits to what our drawings are. I've got a focal length here of, what is that, about 2.5. So f is equal to about 2.5. Really, the units don't matter on this case because all the units are the same. It's just looking at ratios, really, just triangles. I got a distance of the image, or a distance of the object, of about 7.7-ish. Distance of the object is about 7.7-ish. And my expected distance of the image is around 3.8, somewhere around 3.8, but we'll just leave that blank now since I don't want to over-specify this thing. So if I've got 1 over f, I've got 1 over 2.5, that's equal to 1 over do, which is 7.7, plus 1 over di. Well, I'm going to have to do a little bit of rearranging here with the math. So 1 over 2.5 minus 1 over 7.7. You notice how this is kind of like parallel circuits or series capacitors? That's equal to 1 over di. And let's see what I get here. So I've got 1 over 2.5, enter, minus 1 over 7.7, enter. And I'm going to raise that to the negative 1 power. So if I inverse it, I get about 3, or I'm going to say that, di is about 3.7. And I think we said around 3.7 earlier, right? So there we go. It's about 3.7. And that matches up. So the math works here. Now let's do one more, just so we can say we did it. If we deal with, let's say we deal with one of these virtual ones. Let's do this one. Just go to the next one. Or actually, let's do this convex one. So if we have the convex one, then we have a distance of the image of around, that's about 3.8. Let's call it 3.8. So distance of the object, right? Distance of the object is around 3.8. The distance of the image, we're going to expect it to be around 2.3. So that's going to be, let's mark that, see if we're right or not. But we do have a definite distance of the focal, and the definite distance here is going to be about 5.1. So 5.1, so f is equal to 5.1. But one thing to notice is that f is on this side of the mirror. That's the virtual side. That's the negative side. So we'll put a negative there. So let's see. I got 1 over f, negative 5.1 is equal to 1 over do, which is 3.8, plus 1 over di, which is what we want. And then I'm going to move stuff around. So let's see. I've got 1 over negative 5.1 minus 1 over 3.8 is equal to 1 over di. And got 1 over negative 5.1. Enter, minus 1 over 3.8, and to the negative 1 power gives me about 2.1-ish di, or 2.177. I'll take the extra because, you know, we're supposed to get 2.3. So we're pretty close. Not bad, but not exactly on there. That's what you get whenever you draw. We're pretty darn close. So anyway, we've got different equations to work with lenses and mirrors. Magnification equation, we've got the mirror or lens equation, and really you got to remember that virtual means that the light's not really going there, and usually with virtual things we're going to use negatives. So I'm going to go ahead and stop this video and upload it to Google Drive and give you guys a QR code that you can scan from the sub tomorrow.